What problem does the proposed method SUPRA aim to solve in the context of sequence modeling tasks?
The proposed method SUPRA aims to solve the problem of efficiently uptraining large transformers into performant RNNs in the context of sequence modeling tasks. It addresses the challenge of the linear transformer's instability and poor performance when uptraining large-scale models by replacing softmax attention with a linear kernel and a normalization strategy. SUPRA leverages high-quality pre-trained transformers, linearizes them using a fraction of pre-training data, and fine-tunes them into RNNs. The method aims to bridge the gap between the strong performance of softmax transformers and the efficiency of linear transformers, particularly in long-context natural language understanding tasks. By addressing issues with normalization stability and incorporating modern relative positional encoding schemes, SUPRA offers a simple yet effective approach to converting transformers into RNNs while maintaining competitive performance.
How does the proposed method SUPRA work in converting large transformers into RNNs? Provide a step-by-step explanation.
The proposed method SUPRA works by linearizing large transformers into RNNs through a series of steps. 1. Leveraging high-quality pre-trained transformers. SUPRA starts by utilizing state-of-the-art transformers pre-trained on proprietary datasets containing trillions of tokens, such as Mistral and Llama 2. 2. Linearization using a fraction of pre-training data. Instead of training linear models from scratch, SUPRA linearizes these pre-trained transformers using a modest fraction of the pre-training data. 3. Addressing normalization instability. SUPRA identifies and addresses the instability in the normalization factor of linear attention by replacing it with a group norm operation, following the approach of retentive networks. 4. Incorporating modern positional encoding. To enhance performance, SUPRA incorporates modern relative positional encoding schemes like ROPE to handle absolute positional encoding better than linear attention. 5. Introducing shared weights and trainable layers. SUPRA adds shared weights between keys and queries and uses trainable layers with a similarity function defined as phi x equals ReLU wx plus b. 6. Training new parameters jointly. The new parameters introduced in SUPRA are trained jointly with the rest of the network, ensuring a cohesive learning process. 7. Utilizing a fixed decay vector. SUPRA employs a fixed decay vector gamma in 0, 1 caret h for h heads, ensuring stable attention computations during training and inference. 8. Implementing recurrent inference at test time. At test time, SUPRA utilizes the recurrent formulation for inference, allowing the converted RNNs to operate efficiently in real-world applications. 9. Comparing performance with pre-trained models. SUPRA demonstrates competitive results with the strongest pre-trained recurrent models, showcasing its effectiveness in converting large transformers into performant RNNs. 10. Addressing limitations and future directions. SUPRA acknowledges the limitations of linear models on long context tasks and suggests exploring advanced recurrent state update rules like gating strategies or higher-order linear attention to further enhance performance in such scenarios.
What are the theoretical benefits of using linear attention in the context of transformers and RNNs, as discussed in the paper?
The theoretical benefits of using linear attention in the context of transformers and RNNs, as discussed in the paper, include the ability to reduce inference cost for language and multimodal models. Linear attention can be expressed as an RNN, updating a state and a normalization factor at each time step, allowing for constant inference cost regardless of the number of generated tokens. This linearization technique establishes a connection between transformers and RNNs, providing a duality where models can be trained with sequence parallelism like transformers, but operate as RNNs at inference time. Additionally, linear attention offers computational benefits and stability advantages, especially when dealing with long sequences and large-scale models. By replacing softmax attention with a linear kernel and a normalization strategy, uptraining large transformers into RNNs becomes more efficient and stable, leading to competitive performance with the strongest pre-trained recurrent models. Overall, the use of linear attention in transformers and RNNs provides a promising approach to bridging the gap between the two architectures, offering a more efficient and stable alternative for sequence modeling tasks.
How are the models evaluated in the experiment section, specifically focusing on the UP-trained models from 1B to 7B, range into RNNs like Llama 2 and Mistral?
The models are evaluated in the experiment section by uptraining a variety of models ranging from 1B to 7B into RNNs, specifically focusing on models like Llama 2 and Mistral. The evaluation includes two settings: standard language understanding benchmarks and long context evaluations. The performance of different architectural choices and training strategies is compared, highlighting the limitations of linear models on various benchmarks and revealing a persistent gap between vanilla attention and recurrence. The base models chosen for uptraining are Llama 2 to 7B and Mistral 7B, with the evaluation showing that the proposed approach outperforms RWKV5 with minimal uptraining and is competitive with a 7B Mamba model trained from scratch on 1.2 T tokens. The experiments demonstrate that the UP-trained models, utilizing the SUPRA approach, maintain competitive performance with strong pre-trained transformers, showcasing the effectiveness of the uptraining technique in converting state-of-the-art transformers into performant RNNs.
What specific results were achieved with the proposed method SUPRA in terms of language modeling and long context evaluations, as presented in the paper?
The proposed method SUPRA achieved competitive results in language modeling and long context evaluations. In terms of language modeling, SUPRA outperformed the RWKV5 model with minimal uptraining and was competitive with a 7B Mamba model trained from scratch on 1.2 T tokens. It preserved performance on most benchmarks compared to transformers and linear models at the 7B scale. In long context evaluations, SUPRA showed that the Mistral SUPRA model preserved some performance at larger context lengths, although it was noted that this might be due to the decay along the context length shortening the effective context. The results indicated a significant performance gap between transformers and linear models, including those UP-trained from strong long context transformers. The study highlighted the need for more sophisticated recurrent state update rules to excel at long context tasks. Overall, SUPRA demonstrated promising results in both language modeling and long context evaluations, showcasing its effectiveness in converting transformers into performant RNNs.
What are the limitations mentioned in the paper regarding the proposed method SUPRA and its comparisons to other models like T2R and Mamba?
The limitations mentioned in the paper regarding the proposed method SUPRA and its comparisons to other models like T2R and Mamba include the following. 1. Performance drop. The paper notes a modest drop in performance across all benchmarks compared to softmax transformers when using SUPRA. This drop could be partially attributed to the lower quality of the data used compared to the pre-training mix for models like Mistral 7B. It also suggests that linear transformers may inherently be less expressive. 2. Data quality. The performance drop in SUPRA models compared to softmax transformers is partly attributed to the lower quality of the data used for training the models. This indicates that the performance of SUPRA models may be influenced by the quality of the training data. 3. Normalization. The paper highlights the importance of normalization in maintaining the performance of the base LLM when uptraining. It mentions that normalization is key for stable uptraining, and the absence or modification of normalization can lead to poor results, as seen in the case of T2R. 4. Stability. The paper mentions that the T2R uptraining method was unstable, resulting in poor performance compared to SUPRA. This instability could be a significant limitation when uptraining large-scale models, as it may lead to suboptimal results and hinder scalability. 5. Model initialization. SUPRA relies on initializing with strong pre-trained transformers, which means that the performance of SUPRA models may inherit any biases or weaknesses present in the base models. This limitation suggests that the effectiveness of SUPRA is dependent on the quality and characteristics of the pre-trained transformers used as a starting point. 6. In-context learning. The paper acknowledges that SUPRA models suffer from poor performance on tasks requiring in-context learning, such as the 5-shot MMLU task. This limitation indicates that linear models like SUPRA may struggle with tasks that demand contextual understanding beyond what they were trained on. In summary, the limitations of SUPRA and its comparisons to other models like T2R and Mamba include performance drops compared to softmax transformers, potential sensitivity to data quality, the importance of normalization for maintaining performance, stability issues in alternative uptraining methods, reliance on strong pre-trained models for initialization, and challenges with in-context learning tasks.